Hello students, welcome to today's lecture on software engineering. Today's lecture topic is software engineering and its models. It is unit number 1 of MCS 213 course. MCS 213 course is part of MCA program and the course title is software engineering. So in this our presentation today focuses on the first unit. Like this every week we will be focusing on a different unit and ultimately we will be covering up all the units. So today's lecture is a very important lecture because it lays the foundation for all the remaining topics in the subject of the software engineering. And software engineering is a very important subject because I don't need to tell you that most of you must be aiming to become software engineers, aiming for a great career in the software development. And you already know that you are doing a lot of programming, or if at all you haven't yet started, at least you know that there is something called programming. Whenever something called programming comes into the picture, the prerequisite for that is writing algorithms. Okay, so without writing an algorithm, you should not attempt to write a program, at least to start with, where the problems are small. For larger problems, when you have to write a lot of code, then there are various methods and tools whom you can employ. However, there are many ways to develop the software. So which way you will be using depends on the problem definition and also the client's requirements. So many things come into the picture. In today's lecture, we will be starting with the definition of the software engineering, and also we will be going through various models. And also if you see that the software development costs are always high. So there will be some companies which will be saying that we will be developing it for a very less cost. There will be some companies which will be saying that this is a minimal cost which is very higher. So basically what distinguishes them from each other, that for the same piece of solution they are quoting different costs. Here comes the capability maturity models. The companies that follow the very high level quality processes are certified at most with SCI CMM level 5. The starting level is SCI CMM level 1, then 2, 3, 4 and the highest level is SCI CMM level 5. We will be briefly discussing this particular topic also in today's lecture. So to start with, let us see the definition of software engineering. So the definition of software engineering is that the application of systematic, disciplined, quantifiable approach to the development, operation and maintenance of software. That is the application of engineering to software. Now let me repeat it. The application of systematic, disciplined, quantifiable approach to the development, operation and maintenance of software. That is the application of engineering to software. And the second part of the definition is that the study of approaches in A. So basically this definition is having two parts. In the first part, there are three key words: systematic, disciplined and quantifiable. It means that whenever work is assigned, the work needs to be fulfilled or the tasks needs to be completed in terms of stepwise processes. And that is possible only when you apply a particular software development lifecycle model. Whatever it is, the most important is that the process should be systematic in nature. It cannot be arbitrary in nature. The second one is disciplined. So there will be some conventions that you have to follow when you develop the software, which may be the part of requirements of the client. All those things you have to do. And in software development companies, you always have backups also. Like if one employee leaves the company, immediately another will take his position. Okay, in case of long leaves. So it is basically a disciplined approach. Okay, so disciplined approach to software development includes enough of paperwork before each and every task that takes off while developing the software. And again, once you go to the software, once it's tested and once it's installed, then comes the maintenance into the picture. And prior to the maintenance, operating that particular software. So software operation, software maintenance. These are very critical activities. Most of the amount is spent on software maintenance for the simple reason that the requirements keep on changing from time to time. Okay, why the requirements keep on changing from time to time? Because the underlying rules and regulations keep on changing from time to time. Whenever some rules change, you have to again change the software also. Also, whenever there are changes in the business dynamics, even then you have to change the software. Whenever you see a competitor offering the same service in a better manner, you may study it and then you want to upgrade your software. All these things fall under the part of maintenance. So normally the maintenance cost is very high in most of the software. So the application of systematic, disciplined, quantifiable approach to the development, operation and maintenance of software, that is the application of engineering to software, and the study of approaches for fulfillment of A. These two sub-definitions form the part of the definition of software engineering. Now, from where the software engineering had come, what is its evolution? To start with, in 1960s, we have only machine code. Some of you must be well versed with machine code, because when you are using microprocessor programming, I mean when you have pursued the programming using microprocessors in any of your earlier programs, you will be knowing the machine code also, because the equivalent hexadecimal code and other things will be having switches mapped, and you will be doing the programming using microprocessors in a different way. Basically, it starts from the assembly language. Okay, there are two steps. Assembly language you will be programming, and then it is converted to the machine code. So 1960s, mostly it's machine code. In 1970s, it is higher order languages, like high level languages. You have C language, Fortran, all these things. Then in 1980s, the project development had started. In 1990s, it has become to reuse the software that was developed. So it means that, for example, to sort a list of numbers, I developed a program. That program can be reused in the software wherever there is a requirement for the sorting. So software reuse had commenced in 1990s. Then also in 1990s, wider use of internet has started. Okay, in some countries like in India, I remember it's maybe in 1997, 1998, the internet use started where the speed is in KB. Now we have Mbps speeds and even Gbps speeds. Okay, in 2000, we have the rise of mobiles and the apps. You say nowadays everything is available in the form of app, mostly. And there are some companies which totally moved to mobile apps. They don't have a website. They have a website, but most of the functionality is put in the app. Like let me say Ola is there, it's an app. Uber is there, it's an app. Myntra is there, it's an app. Like that, most of their functionalities are available in the app rather than their websites. Now let us see where the software engineering starts. Until now we have seen from 1960s to 2000s, including even now if you consider 2025. Now we have AI, we have cloud computing. So these things are the current trends. So after the mobile and mobile apps, which are there still now, the current era is focusing on artificial intelligence, cloud computing and other technologies, and with this had also come some disciplines such as cyber security to take care of the security related issues, because you are using internet for many of the critical things, including financial transactions. Now let us see why software engineering is important. Software engineering is important because it addresses very important questions. Some of the questions are, what is the best approach to the design of software? It's not that at classroom level you are writing a program. Let me say I said that write a program to search a particular value in a given list of numbers. So you will write it. You don't think much about it. Okay, but as you are growing, as you are writing many lines of code, and once you are doing your internships, or even when you are doing a project as part of your BCA and MCA programs, and when you start doing project in real life, then it is not so easy that you write the algorithm and you implement the code. There, first of all, you have to decide which approach you have to take to develop the software. Okay, because at that time maybe you are not the only member who is working on that particular software. You might be having a team of 100 people, 1000 people, even 5000 people working on a single piece of software to be developed as a solution to a problem. So what is the best approach to the design of the software? That is one question. Why the cost of software is too high? Okay, for optimal cost, you use the software engineering principles. Why can't we find all the errors? This is a question which does not have an answer till date, because an error occurs when it occurs. That's it. There are some errors which led to loss of lives also, because you can't really test any software in such a way that you cannot give guarantee that there will be no errors. An error may occur anytime, particularly in the real-time software development. When the software is put in operation, that error may creep in at some point of view based on the scenarios. So why can't we find all the errors? But yes, most of them you can cover provided you follow the principles of the software engineering. Why is there always some gap between the claimed performance and the actual performance? Yes, wherever the performance is prescribed, there it is essential that the performance targets are met. The reason is that if you don't meet the performance requirements, then that software is not treated as a functional software. A software fulfilling the requirements means that it also meets the performance requirements. Not only performance requirements, any requirement, whatever is part of that document where the requirements are listed and where the requirements are signed off. Now let us see what are the different approaches to software development. One is build and fix model. Here you directly develop some code, then fix the code until the customer is satisfied, and then you deliver the product. It is perfectly suitable for a very small lines of code. Now let us take one example. You are finding the factorial of a number. Okay, you have written a program for it. So somebody will be coming to you and asking you to run the program and show. Okay, you have run it. Then they will say, okay, now do it for the number 1500. Then your program may not run based on the style of your coding. Suppose you have written your program only for first 100 numbers, then it will not work for 1500 direct. Then they may say that no, it should work. Then you might be doing some correction to your code such that it works until that number. So once it works for that number, and if that is the requirement, then your program is completed. Your task is completed. So you will be delivering that particular product. Okay, this is only an example. Basically, it never happens for such smaller things. Okay, but I am just giving you an example that in build and fix model, you develop the code, you fix the code until the customer is satisfied and deliver the product. You can see this particular figure. Directly the first step is you are developing the code. Then you are fixing the code until the client is satisfied. When I say fixing the code, here we are not having an iteration to develop the code because you developed the code. Now fixing the code is that making minor changes to your code so that it fulfills the requirement of the customer. And then ultimately you deliver the product. So the three steps in build and fix model are develop code, fix the code until the client is satisfied, and then deliver the product. Now comes one of the popular models of the software engineering. But then there are many drawbacks to this model also. That is waterfall model. You know the waterfall, okay? How a waterfall looks like. It falls from higher point to the lower point, okay? But in the name itself, you have waterfall. So you will never see any water moving from downward stream to upward stream. It always moves from upward stream to the downward streams. That is why it is called fall. So in waterfall model, you have many steps. The first one is requirements analysis, then comes design, then comes coding, then comes testing, and then comes maintenance. Quite interesting part of this particular approach is that after you move from analysis to design, you can only move to coding, you cannot go back to analysis. After you move from design to coding, you cannot go back to design. You cannot go back to analysis. You can only go to testing. You can't even go fast forward to maintenance. So, the feature of this particular waterfall model is that it is a stepwise process where you cannot skip any step. You cannot move in the opposite direction also. So, one very important thing about this model is that the client had given you the requirements. Now you have to develop the design document. During the time, if the client says that I have a new requirement, you will say, sorry, I can't help. Okay. Once a particular step is completed, it is final. There is no way for you to relook. And any software that follows the waterfall model is bound to have not very long life, because requirements change is a continuous process. So after the product is delivered, even while the product is underway, if there is any change in the requirement, the software will not take it, and obviously the software, even after its completion, it cannot be deployed. In those cases where the software is deployed, even then the chances of its running for longer times are very less, because at some point there will be a change. Let me say even the platform change. Okay, a new language had come which can run faster on some latest machines. So you have to throw the software out. But still that doesn't fall under the approaches to the software development. But the main thrust is on requirements. Requirements keep on changing. Even a better way of looking at the things, if at all not exactly the requirements. Okay, but no change can be done in this particular software if it is strictly confining to the waterfall model. Now, many companies use a modified version of the waterfall model. They took the model, but they made it amenable for their own requirements. So here what they have done is that they created a feedback within the model. So the model is that waterfall model with feedback, requirements analysis, design, coding, testing and maintenance. Here what you find is that it is possible to move from one phase to another phase. Like that you can get feedback and ultimately you will be completing your software deployment. Now the next model is iterative enhancement model. Here waterfall model is applied in each iteration. So waterfall model is completed, you have the end product. Now again waterfall model is applied. Okay. So like that in each iteration you will be using the same model, and again you start from step 1 and go until step 2. This is iterative enhancement model. Then one very important model after waterfall model is prototyping model. This is the model where the client says that I want software to be delivered very fast. So here what happens is that a very quick plan is made, a very quick design is made, a prototype is developed. What is meant by a prototype? It is basically a working model of the software to be built. Like you made a very sample, people say sample flat is ready, you can have a look. Okay, something like that. So you can develop the prototype and then you deliver it to the customer, and the customer gives you feedback. Then again you plan for it, design it, and again develop prototype. And like that, after the iterations, what happens is that the final version of the software will be ready, and that will be delivered, and where there will be no further feedback. This is called prototyping model. The features of prototyping model are that it helps in determining user requirements more deeply. At the time of actual product development, the customer feedback is available, and it does consider any types of risks at the initial level itself. One of the Important software development approaches again is spiral model. The objectives are set for the particular phase of the project. The risks are identified to the extent possible. They are analyzed and necessary steps are taken. Based on the risks that are identified, the software development lifecycle model is selected and is followed. So, at this point, the work done till this time is reviewed. Based on the review, a decision regarding whether to go through the loop of spiral again or not will be decided. If there is need to go, then planning is done accordingly. So, this is the schematic which helps you understand the spiral model. You can see the development itself looks spiraled. Okay, there are various steps. The steps keep on or getting repeated during the each phase. Now, the final software development model is that rapid application development. This model gives a very quick approach for software development and is based on a linear sequential flow of various development processes. The software is constructed on a component basis, so multiple teams are given the task of different component development. It increases the overall speed of software development. It gives a fully functional system within very short time. This approach emphasizes the development of reusable program components. It follows a modular approach for development. The problem with this model is that it may not work when technical risks are high. So, today we have seen different approaches to the software development. These are basically the models of software development or software development lifecycle models. In the next session, we will continue with the remaining topics of this unit as well as the next unit of MCS 213. Thanks a lot.